Somewhere between Beijing and Shanghai, a fiber-optic cable is carrying something that no classical network has ever moved. Encryption keys whose security is guaranteed not by an algorithm, but by the behavior of individual photons. If an adversary intercepts one of those photons, the quantum state is disturbed and the key is gone. That network is live, it spans thousands of kilometers connecting major cities, and it extends into orbit via a satellite link that bridges distances ground fiber cannot reach economically. Meanwhile, the Western bet looks entirely different. No new cable, no photon sources, no cryogenics, just new mathematics, baked into software updates, running on the same internet that already exists, two architectures, one problem. How do you keep a bank transaction, a power grid command, or a hospital record secret when a quantum computer can eventually crack the locks everyone currently uses? The odds on which approach actually wins are closer than either camp admits, and they just moved. Price each bet on 4 dimensions. Does it work at scale right now? What does it cost to spread across a real network? How far can it reach? And how durable is the guarantee it offers? The two wagers are a physically sovereign security architecture built on quantum mechanics and a mathematically sovereign one built on problems that quantum computers are believed to find intractable. The first bet, call it the physical bet, rests on a fact from quantum mechanics, rather than an assumption from number theory. A photon cannot be copied without disturbing it. That is not a conjecture waiting to be refuted by a clever mathematician. It is the no-cloning theorem, and it has held up across decades of experimental tests. China has built a ground fiber backbone using this principle, connecting major financial and government nodes with peer-reviewed publications from the operating research groups describing key rates and link distances that place this firmly in the category of a working system rather than a laboratory prototype. A satellite-to-ground demonstration extended the reach beyond what fiber allows, delivering key exchange over distances that make this something more than a city-to-city curiosity. The wager is that a tier of data exists, state communications, financial clearing, critical infrastructure commands, for which an unconditional physical guarantee is worth the capital cost of dedicated infrastructure. Think of a photon carrying a quantum key as a soap bubble, carrying a note. The only way to read the note is to pop the bubble. Once popped, the note is destroyed and the recipient receives an empty space instead of a key, and knows immediately that someone was listening. Classical encryption is different. It is a padlock box whose lock can eventually be picked given enough time and computing power. The second bet changes the lock to one that is believed to resist quantum-powered lockpicks, but it is still a lock. The physical bet removes the lock and replaces it with a bubble. The second bet, the mathematical bet, rests on a multi-year process run by the United States National Institute of Standards and Technology, involving cryptographers from dozens of countries, designed explicitly to surface weaknesses before standardization rather than after deployment. The surviving algorithms based on lattice problems and hash-based constructions were selected because the global cryptographic community's best current read is that quantum computers cannot solve these problems efficiently. These algorithms run as software updates. They require no new hardware for most use cases. They can protect a mobile device in a remote region as readily as a data center in a major financial hub. The coordination problem of updating 1 billion devices is real, but it is logistical, not physical. The first weighing is on what is actually working today. The physical bet is operational in a meaningful sense. Peer-reviewed publications and corroborating reports from independent researchers describe China's backbone carrying real traffic between financial institutions and government endpoints. The mathematical bet is rolling out. The National Institute of Standards and Technology finalized its first post-quantum standards, and major technology vendors have begun integrating them into browser handshakes and cloud services in hybrid mode, meaning they are protecting real traffic today even before the migration is complete. Hybrid deployment figures come from vendor announcements rather than independent audits, so treat them as directional rather than precise. The physical bet leads on proof of existence for the high security tier. The mathematical bet leads on breadth of current reach. The line moves slightly toward the mathematical bet on the dimension of working for most users right now, while the physical bet holds a genuine advantage for the specific endpoints it covers. The second weighing is on cost and deployment reach, and this is where the pricing gets stark. The mathematical bet's deployment cost is close to marginal. Software updates are cheap. The lattice-based algorithms that the National Institute of Standards and Technology standardize run efficiently on existing processors, requiring no hardware replacement for the vast majority of use cases. Spreading a new mathematical standard across 1 billion devices is a coordination challenge, not a capital infrastructure challenge. The physical bet's cost structure is categorically different. Quantum key distribution requires dedicated fiber with relay nodes at intervals of roughly 100 kilometers or less, because photons degrade as they travel and cannot be amplified the way classical signals can without destroying the quantum information they carry. That constraint is not a current engineering limitation that will be resolved by better manufacturing. It is a consequence of the physics the bet is built on. Each relay node is a capital expenditure and a potential attack surface. Satellite links extend range but introduce atmospheric losses and require ground stations. The physics of photon loss in fiber is well established and not in dispute. Independent analyses of deployment cost per kilometer consistently describe the physical approach as orders of magnitude more expensive than software-based alternatives. Here is the loss that needs to be priced flat without softening it. The physical network, real as it is, covers a small fraction of the endpoints that need protection. A regional bank branch, a hospital in a secondary city, a shipping logistics node, a municipal power authority. None of these are on the physical backbone, and there is no credible near-term path to connecting them. On the metric of how many endpoints can actually be protected, the physical bet loses to the mathematical bet, and the margin is not close. That is the loss. The elegance of a physics-derived guarantee does not close the coverage gap, and pricing it any other way would be reading a press release rather than the evidence. The third weighing is on the durability of each guarantee. The physical bet ceiling is genuinely high. If the implementation is correct, an adversary with unlimited computing power, classical or quantum, cannot recover the key from intercepted photons. The guarantee does not expire when computational resources increase, but the guarantee is only as strong as the implementation, and implementations have been attacked, not by breaking quantum mechanics, but by exploiting imperfections in the physical hardware, detector blinding attacks, timing side channels, flaws in random number generation. Academic literature documents several such attacks against commercial quantum key distribution devices. The pattern has been attack demonstrated, device patched, new attack variant found. The community treats this as an ongoing arms race between hardware hardening and attack discovery, not a solved problem. The physical bet's theoretical ceiling is real. Its practical floor is messier than proponents typically acknowledge. When implementation risk is priced alongside mathematical risk, the line on durability moves back toward rough parity between the two bets. The fourth weighing is on the mathematical bet's own durability, and the honest pricing here requires facing what happened during the National Institute of Standards and Technology process itself. One candidate algorithm was eliminated not by a quantum attack, but by a classical one. A conventional computer running an unexpected algorithm broke it. That is the scenario that reprices the mathematical bet most sharply, not a quantum computer finally reaching sufficient scale, but a mathematical insight that nobody anticipated. The finalized standards have not been broken. But cryptographic history includes algorithms that survived years of scrutiny and then fell. Not yet broken and unbroken in principle are different odds. The community's published assessments of the surviving algorithms are cautiously optimistic rather than certain, and the cryptographers who produced those assessments would be the first to acknowledge the distinction. The classical break of a candidate during the process is the single strongest piece of evidence for the skeptical position on the mathematical bet. It does not damage the finalized standards directly, but it demonstrates that the threat model is wider than quantum attacks alone, and that mathematical assumptions can fail in non-quantum ways. The line on the mathematical bet's long-term durability moves toward caution. A quantum key distribution photon can travel through fiber for roughly the distance between two neighboring cities before degrading beyond use. Unlike a classical signal, it cannot be amplified without destroying the quantum information it carries. Every relay point between origin and destination must be a secured facility that decrypts and re-encrypts the key, which means every relay is a potential attack surface and a permanent operational commitment. Running a continental quantum key distribution network is less like laying a cable and more like building a chain of vaults, each of which must be physically secured indefinitely, each of which introduces a trusted node vulnerability that the unconditional theoretical guarantee does not cover. At the decisive weighing, both bets arrive imperfect rather than one arriving solved. The classical break of a National Institute of Standards and Technology candidate algorithm and the demonstrated hardware side channel attacks on commercial quantum key distribution devices together accomplish that pricing. Three things could still unwind the favored read. First, the physical bet's hardware attack surface is active, not historical. Patching a mathematical flaw in software is faster and cheaper than re-engineering optical hardware deployed in the field. Every deployment that relies on trusted relay nodes carries a physical security requirement that scales with the number of nodes and never disappears as a cost. Second, the mathematical bet's foundations, while peer-reviewed and carefully selected, have not accumulated decades of adversarial scrutiny at the scale of current deployment. The classical break during the selection process was a warning that the threat model for these algorithms is wider than quantum attacks alone. A fundamental break of a finalized standard, while not assessed as likely by the cryptographic community, would require emergency migration of an enormous installed base of systems that are historically slow to update. Third, neither bet addresses the harvest now decrypt later threat symmetrically. Adversaries who are storing encrypted traffic today to decrypt once a sufficiently capable quantum computer arrives are most effectively countered by the physical bet for traffic on active quantum key distribution links right now, and by the mathematical bet for everything else. But the mathematical bet's protection is only as good as the migration speed, and migration across critical infrastructure is historically measured in years, not quarters. Synthesis. The odds favor the mathematical bet for network scale deployment in the near and medium term. Not because its guarantee is stronger in principle, but because the network it needs to protect is already built, and software runs on infrastructure that already exists. The line sits closer to 60-40 than to 90-10, and the reason the margin is that narrow is the constraint became catalyst dynamic. China's exclusion from the standards bodies and semiconductor supply chains that shape the current cryptographic landscape sent its researchers toward a different question entirely. What if the key never travels as data at all? That constraint produced a deployed network that Western institutions are now studying as a benchmark, which is itself moving the mathematical bet's deployment timelines faster than they would move otherwise. Two concrete results would swing the line next. The first is a quantum repeater demonstration at meaningful distance. Current quantum key distribution networks require trusted relay nodes because true quantum repeaters, devices that can extend a quantum state without measuring and destroying it, remain a laboratory challenge rather than a deployable technology. If any research group in China or elsewhere demonstrates a quantum repeater operating over distances that would replace a significant number of trusted relay nodes in a real deployment, the coverage gap concession would need to be partially repriced. Reports in the field indicate several groups are within experimental range of this milestone, but no independently confirmed result for a deployable repeater has emerged. A credible, independently reproduced demonstration at scale would move the line meaningfully toward the physical bet for the high security tier and expand its geographic reach. The satellite-to-ground link is a partial answer to the distance problem. A ground-based repeater at meaningful scale is the fuller one. The second catalyst is a cryptanalytic advance against one of the finalized National Institute of Standards and Technology algorithms. The standards exist and are publicly available. They are not proven secure. They are currently unbroken by the best-known attacks. A significant result against one of the finalized algorithms, whether classical or quantum, would trigger emergency standardization and force a migration that most infrastructure is not positioned to execute quickly. The probability is not assessed as high by the cryptographic community, but the impact would be asymmetric. It would reprice the mathematical bet sharply downward and move institutional appetite toward the physical bet for any endpoint that can afford dedicated infrastructure. Even a partial break requiring classical computational resources not yet widely deployed would widen the case for hybrid deployments and accelerate serious investment in the physical bet's coverage expansion. A third result worth watching is an independent adversarial security assessment of China's physical network. The published evidence comes primarily from the groups operating the infrastructure and from peer-reviewed papers by associated researchers. An assessment conducted by a credible party without a stake in the outcome, examining the trusted relay nodes, the key management systems, and the hardware supply chain has not been publicly conducted. If that assessment were published and found the network's security posture sound, the physical bet's odds move up and Western institutional appetite for hybrid approaches accelerates. If it surfaces implementation vulnerabilities in the relay nodes, exactly the structural weakness the skeptical read already identifies, the mathematical bet's lead widens and the hardware attack concern moves from theoretical to demonstrated at operational scale. The evidence prices the mathematical bet ahead, not because post-quantum cryptography is proven unbreakable, but because the network it needs to protect is already built. Software runs on what is already there, and the coverage gap between the two approaches is real and wide. The physical bet carries a theoretical ceiling that the mathematical bet cannot match. Physics is a harder guarantee than mathematics, but a ceiling only matters if you can reach it, and for the vast majority of endpoints on the global network, the infrastructure required to reach that ceiling does not exist and is not arriving on any near-term timeline. China's exclusion from the standards bodies and supply chains that shaped current cryptographic infrastructure sent its researchers toward a different question. What if the key never travels as data at all? That constraint produced a deployed network that the West is now studying as a benchmark rather than dismissing as a workaround. The restriction sharpened the physical bet rather than eliminating it, and that sharpening is precisely why the line sits at 60 to 40 rather than somewhere less interesting. The photon still self-destructs when intercepted. The math still has not been broken. Both facts remain true simultaneously. 2 bets, 1 deadline, and the question the network actually asks is not which architecture carries the more elegant guarantee, but which one is protecting real traffic at real scale before the adversary's quantum computer arrives. On that question, the line continues to move, and the direction is not yet final. Which bet would you back for the infrastructure that matters most to you? The physics guarantee that cannot reach most of the network, or the mathematical assumption that can reach all of it? The comment section is the market. Subscribe if you want the odds updated when the next result lands, because in this race, the line moves faster than the headlines do.